Hey there, and welcome. Have you ever stopped to think about how your computer can run these massive programs? Huge video games, complex software that are gigabytes in size, when it only has a fraction of that in its super fast memory? It seems impossible, right? Like trying to fit an elephant into a shoebox. Well, today we're going to pull back the curtain and unravel this incredible magic trick.
So here's how we're going to break it all down. First, we'll tackle the core problem itself. Then we'll look at the first genius idea to solve it, a little something called paging. After that, we'll see how that solution created its own giant new problem and explore two really clever ways to fix that, one by making an index for your index and the other by, well, flipping the whole idea on its head. And finally, we'll get into the big trade-off between speed and space.
Okay, so at the very heart of how your computer works, there's this constant battle going on, a fundamental conflict between the need for speed and the simple reality of limited space.
I mean, seriously, think about it. The apps we use every single day are absolutely huge. We're talking gigabytes and gigabytes of code, data, you name it. So how on earth does your computer manage to run all of that without just completely grinding to a halt?
And this right here, this is the whole issue in a nutshell. The programs we want to run are these massive gigabyte-sized things. But the super fast memory, the RAM, where the CPU actually does its thinking, it's way, way smaller. Your computer literally cannot load an entire program into that fast memory all at once. You just can't do it.
So how does this system get around this impossible problem? It uses this really elegant solution called paging. You can think of it as a very, very clever librarian's trick.
First off, the computer gets smart. It doesn't even try to load the whole program. Instead, it takes that giant book of a program and breaks it down into thousands of small, identical-sized chunks. And these chunks are called pages. Each one is just like a single chapter.
Now, on the other side, you've got your physical RAM. It's also divided up into slots of the exact same size. These are called frames. And just like our analogy, you can think of them as the empty slots on the library shelves, perfectly sized to hold exactly one chapter.
Okay, so how does the computer know which chapter is sitting on which shelf? It uses something called a page table. This is basically the system's card catalog. It's a big index that keeps track of exactly which program page is currently sitting in which memory frame.
But here's the twist. This super clever solution, it actually creates a brand new problem, and it's a big one. What happens when your card catalog becomes as big as the entire library?
As our source material points out so well, if a program has millions and millions of pages, its page table, that index we just talked about, can become absolutely enormous. It turns into this giant address book that, well, you have to store somewhere.
And just to put a number on it, for a pretty typical 4 gigabyte program, which is nothing special these days, the page table alone can be 2 megabytes in size. And here's the real catch. The computer needs to store this page table in that fast RAM to actually use it. But a single memory frame is usually only about 4 kilobytes. A 2 megabyte page table simply is not going to fit into a 4 kilobyte frame. So we're right back where we started, facing another space crunch.
This problem sent engineers back to the drawing board, and they came up with a couple of even cleverer solutions. Two main ideas popped up. One was to just make the index smarter, and the other was to, rethink the whole idea of an index from the ground up.
All right, let's look at the first approach, which is called multi-level paging. The idea here is just brilliant in its simplicity. If your index is too big, you just create an index for the index.
So here's how it works. You take that massive 2 megabyte page table and you chop it up into smaller pieces, where each piece is small enough to fit neatly into a memory frame. Then you create a new, much smaller master index called an outer page table. And all this little master index does is tell the computer where to find the different pieces of the main index. Simple, right?
But there's another, much more radical way to solve this. This approach is called inverted paging. And the idea is, instead of each program trying to keep track of where all its pages are, what if the system just kept one single list of what's on all the shelves? So just as a quick refresher, a normal page table belongs to one program. You look up a page number, say page 1, and it tells you, yep, that's in frame 9. Every single program running on your machine has its own table, and all those tables take up a lot of space.
Well, inverted paging flips this whole thing on its head. There is only one table for the entire computer, a global page table. And instead of being organized by page number, it's organized by the physical frame number. So now you look up frame 1, and it tells you, oh, that slot is currently being used by page 2 of program B.
The advantage here is just massive memory savings. You go from having maybe hundreds of page tables down to just one. But, and it's a big but, there's a huge drawback. To find where, say, page 4 of program A is, you can't just look it up anymore. You have to search the entire table one entry at a time until you find it. And that makes searching much, much slower.
This brings us to the core of so much in computer science and engineering. There's almost never a single perfect answer. It's always about making trade-offs.
And this table just lays it all out perfectly. Normal paging is super fast, but it's a memory hog. Inverted paging sibs memory, but boy, is it slow. And that multi-level paging we talked about, well, that's your happy medium, the compromise right in the middle. It's all about what you want to prioritize.
As the source material puts it so beautifully, our priorities have really shifted over time. Memory just keeps getting cheaper and more plentiful every single year, but our time doesn't. And that economic reality has a huge influence on which of these trade-offs gets chosen in the real world. Most of the time, speed is king.
Which leaves us with one final question to chew on. In a world with nearly infinite data and hardware that gets cheaper by the second, we've pretty overwhelmingly chosen speed over space. But as our needs change, especially with mobile and low-power devices, will that always be the case? Or will the pendulum swing back, forcing us to invent even cleverer ways to manage that one precious resource, memory? Something to think about. Thanks for tuning in.